Hello, everyone. Good morning, good afternoon, good evening, depending on where you are. I'm Zhen Chen. I'm a professor in mechanical engineering at Peking University in China. Today it's our great pleasure to have Professor Joe Lefkowitz here to give a lecture. Please allow me to briefly introduce Professor Lefkowitz. Professor Joe Lefkowitz received his bachelor degree from Johns Hopkins University in 2009 and his PhD degree at Princeton in 2015. He spent 2 years as an NRC research associate at the Air Force Research Laboratory. In 2017, he joined the Faculty of Aerospace Engineering at Technion E3 Institute of Technology. Currently, he is the Zuckerman Faculty Scholar, a recipient of the Hanning Prize for Young Researchers granted by the Technion Faculty of Aerospace Engineering. He is a member of the editorial board of Combustion Flame. His research interests including ignition, plasma acid combustion, plasma chemical conversion of alternative fuels, hypergelic ignition of solid fuels, and the infrared optic methods for sensing and the imaging of reactive flows. So today he's talk about a new approach to ignition, minimum ignition power and the interpulse coupling, a topic I'm sure very interesting to all of us. So with that, Joe, please, I give the floor to you.
All right, thanks, Zheng. It's nice to see you all. It's nice to give a talk to such a broad audience, and I really appreciate the combustion webinar and Yiguang and Wenting and the rest of the panelists for all the hard work they've done. So as Zheng mentioned, I'm presenting on a new approach to ignition, minimum ignition power, power being the different word there, and interpulse coupling, which I'll explain. Before that, I know Technion is not the most well-known university internationally, so I thought I would introduce it. We were founded in 1912 as Israel's first university. Calling it Israel's first university is interesting because actually in 1912, Israel was part of the Ottoman Empire. And so the university was founded before Israel as a modern nation was founded. Our vision aims to be a science and technology research university among the world's top 10, dedicated to the creation of knowledge and the development of human capital and leadership for the advancement of the state of Israel and all humanity. It has a rich history. It was founded with the help of Albert Einstein, who you can see pictured here with the first Technion Society. You can see a picture of our university here. Aerospace engineering is up on top of the hill over here. And our department was founded in the 1950s with help from Professor Theodor von Karman. So a little bit of history of Technion. We're located in Haifa, which is a beautiful city on the Mediterranean coast. You can see I've chosen to use a similar picture to this one as my background. It's a really nice place. For anyone who may be visiting the area, I hope you drop by. I'd be happy to have anybody. So this is our laboratory. We were founded in 2018. You can see my group members here. This is Sam Nath, C. Shen, Natalie Rosen, who's since left, Iker Lasso, Karen Linschitz, and Gali Feingold, my students and postdoc. We just opened our laboratory a few months ago in 2020, and it's already packed with a lot of stuff and clutter. So we are functioning now, finally open. So today I'm going to present on a collaborative effort bridging 5 years of research, which actually began during my postdoctoral work while I was at the Air Force Research Laboratory under the advisement of Dr. Timothy Umbrello. This is just the listing of the group members who have worked on the presentation I'm going to give. So here at Technion, it's myself, Dr. C. Shen, Iker Lasso, and Natalie Rosen. The Air Force Research Laboratory, you can see a broad team, but primarily it's Timothy Umbrello, Stephen Hammock, Campbell Carter, new addition Joshua Gray, and then Steve Adams, Jared Miles, Bob Lewicki, and Ken Busby have collaborated on various parts of this. You can see our partners at University of Dayton, University of Oregon, Purdue, and University of Central Florida here. So this is going to cover these 7 publications. I list them here, so I don't need to list them throughout the presentation, but if you're interested in more information, please refer to any one of these papers for specific parts of the presentation. And of course, acknowledging our funding partners. All right. So plasma-assisted combustion, I just want to put together a few highlights. Everybody is relatively familiar with this area by now. I was part of the colloquium co-chair group at the most recent proceedings of the Combustion Institute. We had roughly 90 submissions there, and about a third of them were in the plasma-assisted combustion area. So in the new concepts colloquium, at least, this is the largest subgroup of papers. Maybe one day we'll have our own colloquium, I don't know. As Guang and I were talking about even before we started here, there's been a pretty big increase in funding recently, especially in the US, with recent grants from DOE, DOD, NSF, and other funding organizations. And a lot of the national labs are involved in these, such as the Air Force Research Lab, the Army Research Lab, Sandia, Argonne, and I'm sure there's others. Those are the ones that came to mind, as well as, of course, dozens of universities. All right. So I want to begin with how I understand forced ignition. It all begins with a plasma discharge, where all we do is we apply a voltage and a current waveform to electrodes. The way that we apply that and the geometry of the electrodes determines the energy deposition, distribution, and schedule. That in turn informs the temperature, whether it's electronic, vibrational, rotational, translational, maybe in equilibrium, most usually not in equilibrium for the studies that are of interest now, as well as the number density of species, both spatially and temporally. And the number density of species, of course, involves electrons, ions, excited species, radicals, as well as our neutral species that we're all accustomed to. Then depending on both the energy distribution and the temperature and species distribution, you get a plasma geometry, which can have its own induced flow. And that induced flow field may be dominant. For example, in quiescent ignition, the induced plasma flow field is one of the dominant characteristics determining the ignition dynamics. Of course, this couples into the combustion kinetics. This part I think the community knows best, and the 2D laminar flame growth dynamics. Of course, Zheng Chen and Guang on this panel would know plenty about that. Then this then couples into the turbulent effect on kernel development. So once we understand the laminar flame growth dynamics, we can move on to the turbulent flame growth dynamics, then bulk flow effects, non-premixed and stochasticity in the mixture ratio, then to multi-phase ignition. Finally, to the effects of flow recirculation and limited residence time. This is really the bulk flow geometry. And then we can understand full-scale engine ignition. So the reason I draw this spiral is to show you the different spatial and temporal scales involved here, going from the nanosecond time scale here, even single nanosecond time scale, all the way out to tens of milliseconds. So we're not going to focus on all of these subjects today, but what we will focus on is a broad range of them. So we'll look at how the applied voltage and current waveform determines the energy deposition, distribution, and schedule, and how that affects the temperatures, species, and geometry. Then we'll jump way ahead to the effects of flow and how they couple together with those first four subjects. And we'll talk a little bit about recirculation time and then full-scale engine ignition. So how do we think about ignition optimization? Rudolf Maley in the 1980s was one of the first to perform a really detailed analysis of how to optimize ignition. He said you should deposit the energy in the shortest possible time, which creates an expanding plasma volume with the highest possible surface velocity. This reaches the largest possible plasma radius, which then couples into, of course, what we know as the critical radius. And by creating a large plasma radius, you can achieve the critical radius as soon as possible. And you don't want to supply additional energy after the flame is propagated beyond the plasma radius, because this additional energy never makes it to the flame front, so it's wasted. So he proposed to use a nanosecond plasma, or a what he called a breakdown plasma. So the breakdown occurred here in the first 10 nanoseconds. And then he explained, and they showed experimentally, that as you continue supplying a high voltage and current, what naturally happens is you enter into kind of a spark regime, which is high temperature, but lower current. And then as you continue, it enters into a glow regime, which is lowest current. So you have the highest power deposition here by an order of magnitude. And he theorized this is the most efficient way to deposit energy, and also showed that you don't have deleterious effects of electrode heating that you have from longer duration spark or glow discharges. This makes sense for a quiescent environment, but what about a flowing environment? We know that in IC engines, we have 1 to 10 meters per second flow rate. As we move on to gas turbine combustors, we have 10 meter per second flow rate. And then in scramjet cavities, which was the original motivation for this work, you can have up to 100 meter per second flow velocity. Now, if I look at a quiescent ignition event, even in high turbulence, I end up with a kernel that essentially propagates out from the center. However, if my local bulk velocity exceeds my flame speed, I get something like this picture, which was proposed by Bilal and Lefkowitz, like almost everything else in ignition, in 1975. And what they showed, or actually what Maley showed, is if I do have a flow, my ignition kernel for a long discharge can be elongated like this. And so the idea that the best way to deposit energy is by having a plasma volume that expands as quickly as possible or accesses as large of a volume as possible can be thought of differently when the volume is expanded by the flow itself. And in that case, maybe there's a different way to optimize ignition. But there's a problem. So in a quiescent mixture, like I said, short discharge is the best way. But on a long time scale, maybe the best way is a long discharge. This was tried early on by a paper by Kono in 1985. And what they showed, and what you can see here in the voltage and current waveform, is when you try to apply a long duration discharge, which would look like this at 0 meters per second, which is kind of a square wave in terms of power. Even at 7.3 meters per second, you get this increase and snap back, increase and snap back. And what's happening here is the arc is being blown downstream and then is being reinitiated at the electrodes. The overall effect of this is that you get individual ignition kernels and you're not actually depositing the gas into, depositing the energy, into a single ignition kernel. And so you couldn't really see the benefits that Bilal and Lefkowitz proposed. In addition, the energy deposition, as we said, occurs on the 10 nanosecond timescale. And by continuing the discharge at these long durations, you run into the problem of you're operating in this spark to glow regime, which is less efficient. So, spatial fluctuation solution, what can we do about this? We can increase the energy deposited to activate and engage a larger volume. So spatial fluctuations would occur in a scramjet cavity where we have lots of different turbulent structures interacting with the fuel flow rate. This could cause spatial fluctuations. Also temporal fluctuations. So we propose an alternative solution to the long duration discharge or to the short duration discharge, which is nanosecond pulse high frequency discharges. Of course, we follow a lot of work done in many different groups across the world, whether it's Christoph Loh, who was one of the first to look at NRP discharges, two groups at Princeton and at Ohio State and elsewhere. But our idea was to do it in a flow. So we would deposit short nanosecond pulses at very high frequency, what we call NPHFD, nanosecond pulse high frequency discharge. And we would see if there's different energy coupling there. The benefit of the NRP discharge is it couples energy into the discharge only during the breakdown phase, but it results in a 2 orders of magnitude reduction in power required to maintain average electron density compared to a DC discharge. So if I look at just the average electron density, which was done here in this paper from 2002, you can see that my average electron density is about here. And if I compare that to the same average electron density in a DC discharge, the nanosecond pulse discharge can have 2 orders of magnitude less energy. So the first time we looked at this was in a paper in 2015, which was a collaboration with Fred Schauer and John Hoke in the AFRL. And we were looking at a pulse detonation engine. And what we found is that the total energy of the discharge, as it increased, you would decrease the ignition time. We found this in aviation gasoline and ethylene. But the stipulation to that is all of these red points occurred at 10 to 40 kilohertz pulse repetition frequency. We could have the same energy deposition, but if applied at 1 to 5 kilohertz, you would have a longer ignition delay time. And you could also see we compared it to a capacitive multiple spark discharge at 1 kilohertz, which pretty much operated almost exactly the same. And if you look at images of the kernel, what you could see at 2 kilohertz is that you were getting individual ignition kernels, which would break off and then spread on their own. However, at a 40 kilohertz repetition frequency, we saw one continuous discharge that formed a large kernel, and then that obviously had a big effect on ignition. And at that time, we did some simple 0D modeling of the methane air plasma. And we saw that at 40 kilohertz frequency, which you can see here in black, we saw a increase in the average. In this case, we're plotting O atom concentration or mole fraction here. And you could also see a stepwise increase in temperature, which was greater for greater frequencies. And here we didn't have any heat losses or radical losses other than recombination. So it was a very simple model, but we still saw about the same frequencies that we expected from our experiments. So this was the motivation for the work. All right, I'm going to show various results. Broadly, we'll start with parametric studies of ignition probability, kernel growth rate, and comparison with capacitive devices. We'll move on to a proof of concept in a scramjet engine. And then I'll talk a little bit more about the fundamentals, which we looked at in detail with a plasma temperature measurement by optical emission spectroscopy, radical formation rates by kilohertz OH-PLIF, and kernel temperature, which we measured by IR thermometry with a high-speed infrared camera in the mid-IR range. So this is the basic diagram of the experiment, which I'll be talking about for most of the rest of the talk. It's a subsonic wind tunnel with a 38 millimeter square cross section. For all of these studies, except for in the scramjet, we use methane air with velocities from 1 to 10 meters per second, corresponding to a weakly turbulent regime. Our pulses have a 10 nanosecond duration, 10 kilovolt peak voltage. We could repeat them at up to 330 kilohertz. And we saw that on average, we have about 2.9 millijoules per pulse. It was a little different at different conditions, but this is about what it was on average. And our electrodes were in a tip-to-tip configuration or pin-to-pin configuration. And you can see we can control the gap distance by a micrometer. I'll also be talking about the same a similar experimental facility, which we've built now at Technion. This just came online less than a year ago. So not much of our results are from this, but I'm not going to really distinguish because we found almost identical operation between the two tunnels. The benefit of this new tunnel is that we'll have 10 times the flow velocity than the AFRL tunnel. We've installed preheating up to 1000 degrees Kelvin, and that corresponds to a Reynolds number of 300,000, which is very much in the highly turbulent regime. We hope to do liquid injection, which we have not implemented that yet, but this is a future plan. And our ignition source is a little different. Here we have twice the peak voltage, but slightly lower pulse repetition frequency. Okay. So we started out looking at single pulse ignition probability, and we looked at various parameters, equivalence ratio, gap distance, flow velocity, and we looked at the ignition probability after a series of 20 discharge pulses. You can see with the equivalence ratio, we needed to go to higher equivalence ratio or closer to stoichiometric equivalence ratio to get high ignition probability for a single discharge pulse. We could also see a smaller effect of velocity. So in the red, we had 10 meters per second. This line we had 5 meters per second. This line we had 2 meters per second. So actually at lower flow velocities, we needed a closer to equivalence ratio of 1 mixture to get high ignition probability. So after seeing all of these ignition probabilities, we wanted to settle on a base case for the nanosecond-pulsed high-frequency discharge. And so we decided to call this the baseline condition, an equivalence ratio of 0.6, a flow velocity of 10 meters per second. And in this case, we ignited about 1 in 10 times with a single discharge pulse. And so we wanted to vary our conditions around here. So the first thing we did is we had started a flow rate, 10 meters per second, 0.6 equivalence ratio. This was the gap distance. And we had a discharge with 20 pulses. And you could see our pulse repetition frequency here. And I'll introduce this now. One thing I talk about a lot is it's often helpful to think about this in terms of the time between pulses. So below that, I've listed the interpulse time. And so now we can see what these events look like. I hope that video is playing smoothly for everybody. So here we see that all of the discharge pulses are deposited in a relatively short time. They've now stopped here. And we see a very distinct ignition kernel which expands in the horizontal direction quite easily. For these ignition events at lower pulse repetition frequency, you can see that we don't have the same expansion in the horizontal direction. And that's because the Schlieren is imaging a lot of hot gas where this isn't actually ignited. Here we can see that each individual ignition kernel or each individual pulse forms its own ignition kernel. And they just develop as if they were unrelated to each other. And so we've termed these different regimes, the fully coupled regime, the partially coupled regime, and the decoupled regime. So looking at a plot of the ignition probability as a function of the pulse repetition frequency, or the interpulse time, as I like to call it, for different numbers of pulses, we can see a similar characteristic. At high frequencies, we have very high ignition probability, even when we have 2 pulses. So keep in mind, 1 pulse, it was a 10% probability. 2 pulses, now we're up to 100% probability, but only at certain frequencies. As I go to more and more energy, and here it's up to 50 pulses, there are cases where I still don't achieve high ignition probability. Then when I go to even lower pulse frequencies, I can see a wide distribution of ignition probability. And here we call this ignition probability for all of the pulses, right? Not for each one individually. And so what I'm getting there is the single pulse ignition probability times the number of pulses. So here we have about twice the ignition probability of a single pulse, here 3 times, 5 times, etc. And it was just linear. And now it's very easy to separate these into these different regimes. So the fully coupled regime is characterized by 100% ignition probability. The partially coupled regime is characterized by an intermediate ignition probability. And the decoupled regime was characterized by this linear ignition probability with number of pulses. Now, I want to mention I'll be using these regime definitions a lot during this talk, and they are condition dependent. And so for every condition, you can define where the regimes are in terms of PRF or interpulse time space. The result of looking at this is that we can define a minimum ignition power. So we take the 50% probability condition here, and we say, okay, whenever this line crosses 50%, that's the minimum ignition power. And we just multiply the energy per pulse times the pulse repetition frequency. And what we noticed is that the minimum ignition power stopped being a function of the number of pulses. And as number of pulses increases, that's increasing energy. So what we saw is as I increased the energy, this minimum ignition power wasn't changing. And you can see it here, all of these lines bunch up right around here. So there's something happening at this pulse repetition frequency that is not allowing high probability to occur. I could easily get around this, of course, by increasing the power. And so this was a little bit surprising to us, and it caused us to realize in a flowing mixture, you are really worried about the minimum ignition power and not minimum ignition energy. And if you're applying your discharge at a very high power, then you may not see this. But if you can control your power carefully, you'll see that there is a threshold above which you'll have high ignition probability and below which you won't. And that threshold changes with the total energy. But in general, it's much easier to just increase the power rather than increasing the energy, which you can do orders of magnitude and still not, as you can see here, achieve high ignition probability. So this was the first finding, which kind of opened the door to the rest of our studies in this area. We also looked at the flame growth rate as a function of the interpulse time, which is listed here. And you can see this is the shortest interpulse time or highest frequency. And here's the lowest one. And in this case, we were just looking in that fully coupled regime only. We saw that for kernels with this lower interpulse time, there was a much faster growth rate for the kernel, up to twice as fast as compared to the higher frequency cases here. We saw that what was happening is we had a higher flow speed out to a larger radius when we had the lower pulse repetition frequency or the higher interpulse time. And again, we had a 50% reduction in the time to a certain area. So what's interesting about this, as what I mentioned in the previous slide, was that high pulse repetition frequency equaled high ignition probability. But low pulse repetition frequency equals a larger kernel. So there's an optimization here where I want to make sure that I'm in this fully coupled regime where I'm applying enough power to grow a large kernel, but I don't want to deposit that energy too quickly, or else it acts like a single discharge and I do not get the benefits of the flow. And you can see this accentuated in these two sets of images. Here I have the high pulse repetition frequency, 300 kilohertz, and I apply up to 50 pulses. I could see that after 2 or 3 pulses, it looks pretty much the same as at 50 pulses. But if I do that same thing at a pulse repetition of 10 kilohertz, keep in mind, still 100% ignition probability, I can see a pretty drastic increase from 1 or 2 or 3 pulses all the way out to 50 pulses. We also looked at other parameters in the study. So we varied the equivalence ratio, and we saw that these regimes continued to exist at 0.65, 0.6, 0.55. What's happening here is the chance of a single pulse ignition is 0. So there's no real clear decoupled regime like there is at 0.6. I can see the different growth rates here. And what I find is while the plasma's on, all the equivalence ratios grow essentially the same, and all the difference is in the flame speed of that mixture. I looked at the effect of gap distance. What we found is the gap distance plays a huge role in where these regimes are. Or if I go out to 2.5 millimeter gap distance, I actually have a reduced effect of this partially coupled regime. And what that's telling me is that there must be quenching having to do with the electrodes coming into play here. As I go out to a 0.5 millimeter, I end up needing very, very high frequencies in order to get high ignition probability. We also saw that it affected the kernel growth rate depending on the gap distance. And you can see that while I would like to escape the effects of the electrode, I would have to go out to about 5 millimeters. But for our 10 kilovolt discharge, we were limited to about 2.5 millimeters. And to be honest, if anybody has worked with these nanosecond pulse discharges, once you get above 10 kilovolts, you start to have a very high level of electrical noise, which was the reason why the 10 kilovolt discharge was chosen in the first place. Higher than 10 kilovolts, your EMI begins to be a very big problem. So while you could get a higher voltage discharge, and indeed we did at Technion, you still might want to operate in this lower voltage regime. And that would require you to have a smaller discharge gap. We also looked at velocity, and velocity had a very strange relationship with these regimes. So what you can see here is our 10 meter per second case in blue for a 2 millimeter discharge gap. At 5 meter per second, we had this red case here, and our signal pulse ignition probability is lower, so this is lower, but we ended up with a lower minimum ignition power. So at lower frequencies or longer interpulse times, we crossed into this fully coupled regime as compared to 10 meter per second. But at 2.5 meter per second, we saw a very non-monotonic trend where we started at high frequencies, high probability, then somewhere in between the 10 meter per second and the 5 meter per second case, we had a reduction in the ignition probability. And then actually the ignition probability increased again before finally reducing it kind of in line with where you'd expect it from the other two cases. What's actually happening here, and you can see it playing out in this chart, is only at 10 meters per second do I really get the most benefit from the flow. At 8 meters per second, I see it somewhat, but at lower velocities, I can't tell the difference between ignition kernels with 2.5 or 5 meter per second flow rate. And so once you get below a certain velocity, this effect of kernel growth by the flow doesn't really play a role. And in addition, the kernel can propagate upstream a bit because the growth rate is very fast in the beginning. And what we saw here in this non-monotonic case is actually when the kernel went upstream a bit and then we pulsed, this would not help the kernel grow. But once the kernel came downstream and kind of a lobe of that ignition kernel crossed our discharge region again, then we had a high ignition probability and then it dropped to 0. We could look at the minimum ignition power for these as well. So for the 2 millimeter discharge gap case, we saw a very clear rise in the minimum ignition power as we increased the velocity. For the small gap distance, we had a much higher minimum ignition power, and it was not as dependent on the flow velocity. This is because it's dominated by the electrode quenching effect. So what we came up with is a way to control ignition based on this parametric study. So as proposed by Balad and Lafarve, indeed, your ignition kernel grows and the growth rate is determined by the gap distance, as we showed, and the length, which was determined by the velocity times the interpulse time times the number of pulses, or number of pulses minus 1 to get the correct length. But superimposed upon that kernel growth is a thermal expansion rate. And I call it a thermal expansion rate because it's obviously about an order of magnitude faster than the laminar flame propagation rate. And we wanted to assign a single value to that in this parameter here. So what I'm doing here is I'm computing the cross section, which is what we measured with Schlieren, of the ignition kernel at the time of the end of the discharge, including the plasma growth rate, which is in this rectangle, and then the thermal expansion, which is represented by this equation here. And we found very good agreement when we used this thermal expansion rate of 520 centimeters per second. We found we could predict pretty accurately how large the kernel would be at the end of the discharge. And unsurprisingly, when you have a large number of pulses at a high pulse repetition frequency, but not so high, as I said, as to lose the pulse, as to lose the velocity growth effect, you could get a very, very large ignition kernel. And in this manner, you can control over about 3 orders of magnitude the size of your ignition kernel by making use of the properties of the plasma and the flow velocity, which you already have in your engine. More recently, we took a deeper look at the minimum ignition probability. So one thing you didn't see in those slides before is we never changed how much energy we put in with each pulse, which is another fundamental characteristic. So here we saw that we could put in different energies per pulse and get a similar profile with your fully coupled, partially coupled, and decoupled regimes. But if you went to a high enough energy per pulse, you could escape that. Which I think is somewhat intuitive. If I put in a lot of energy in every pulse, eventually I'll get a high ignition probability. If I take the minimum ignition power, though, and plot that, what I find is actually, as I reduce my energy per pulse, I'm also reducing my minimum ignition power. So while going to a high energy single pulse may seem like a good idea, keep in mind that, as I said, you're increasing your electromagnetic interference, you're increasing your electrode wear, and you're also less efficient according to what we found. The most efficient way is to reduce your energy into to the level where you just barely get breakdown. And when you do that, you're able to ignite with the lowest possible minimum ignition power. We also looked at keeping the power constant. So here at 20 watts, we were able to get a high ignition probability most of the time. If we went to 10 watts or 5 watts, we saw a different story. So here I can see the ignition probability at 10 watts as a function of energy per pulse. And I see at this 10 watt case, there are times when I get a lower ignition probability than at the 5 watt case. And what's happening here is I'm changing my regime. So if I'm to the right of this case, I have lower pulse repetition frequency, so it's decoupled. And here I have partially coupled, where in this case, I'm transitioning from fully coupled to partially coupled here. So the minimum ignition power turns out to only be part of the story. You need to be in the correct interpulse coupling range. So I do not want to apply higher energy pulses at a low pulse repetition frequency. This could be deleterious. I'd rather apply low energy pulses at a high pulse repetition frequency. This reduces the minimum ignition power and also ensures that I'm in this fully coupled regime. We also compared to a capacitive discharge system. So here we had our pulse discharge system, and here we have a custom built conventional system where we apply a high voltage and we have a long tail and current, but in the end, we can control the total discharge time and power to some extent. You can see the difference in the time-dependent energy deposition, where with the conventional discharge, I get a lot of energy up front and then kind of decreasing gains as time goes on, similar to what Rudolf Meili stated. Where with the pulse discharge, I have about the same energy deposited with each pulse. Here we matched exactly the conditions, total energy, total time, and therefore average power between the conventional and the pulse discharge case. We also tried cases with different frequencies or different time between pulses as well. Okay, so what you can see here is this case and this case are the matched cases. And we're looking at the growth in the major radius or the longer radius in the axial direction over time. And what we find is that both the green case and the black case, as well as the yellow case, end up to be about the same kernel growth rate. But if I go to this 100 microsecond case, I end up with a faster kernel growth rate, as you can see in the comparison between this kernel and this kernel. So matching the average power and total time duration ended up with similar results for the capacitive and the pulse discharge. But by going to actually a lower power and the same total energy, I could get a much faster kernel growth rate with the nanosecond pulse high frequency system. And so these kind of studies, I just want to comment, are not that common, unfortunately, in the combustion literature, where careful attention is made to match energy and time scale between different methods of ignition. And as you all know, there are many, many, many methods of ignition. And I think we can generally tell that if it's a very high, very fast energy deposition, we might get a large kernel, or if we have a plasma torch, and there's many, many methods. But when you want to compare methods, it's very difficult but important to match all the characteristics that you can in order to have a fair one-to-one comparison. And in this case, we found that if you match them perfectly, the kernels were about the same for conventional and a pulse discharge. But if I go to lower power without changing the energy, then I see the advantage of the pulse discharge because of the longer duration. We also looked at the DRDT, the change in radius with time, and we found that the kernel with the longer interpulse time was growing faster. And that's because it was taking advantage of that 10 meter per second flow. And it really shows the benefit of using that flow velocity to help grow your kernel. Okay, so next we did a proof of concept in a scramjet engine. I'm going to go quite quickly because I've taken a little more time than I intended to. So here we did simultaneous chemiluminescence, OH-PLIF, and Schlieren in a cavity ignition at a Mach 2 scramjet combustor. I have a capacitive discharge here, a low energy pulse discharge event here, and a high energy pulse discharge here. And we're able to compare the growth rates of the different kernels across these three diagnostics. All three diagnostics were operating at a rate of 40 kilohertz. What I find is with a capacitive discharge for relatively low energy, I can only ignite at about a stoichiometric condition. So the fuel flow rate, this would be about stoichiometric. Here it's lean, here it's rich, and this is my ignition time, and my ignitability range is shown on top. For a pulse discharge at 20 kilohertz, it was actually worse than the capacitive discharge. But once I went to 50 kilohertz, I saw that I could greatly expand my range and I could reduce my ignition time. Keep in mind, all of these cases I'm showing have the same total energy deposition. Finally, at the highest frequency, I had the widest range and the no real benefit in terms of ignition time compared to the 50 kilohertz case, but I was able to expand where I had high ignition probability, which is similar to what we saw for the subsonic case. We also could compare between the capacitive and the pulse discharge. So here I saw that there was a limit in energy. I needed to be about above 100 millijoules, similar to what we saw for the minimum ignition power in the beginning. The minimum time to ignition that I could achieve was about 1 cavity cycle time, which kind of makes sense. I saw a factor of 7 difference in energy deposition, but the same ignition time, comparing the pulse discharge and the capacitive discharge. And this was really the benefit of the pulse discharge for the scramjet. So just to summarize, this is the lean limit in terms of energy for the for the capacitive discharge. So I need about 700 millijoules to ignite at this fuel flow rate. Rich limit and minimum ignition energy at stoichiometric conditions. We saw with the for the pulse discharge at 20 kilohertz, it's about the same. When I go to 50 kilohertz, I broaden out those ignition limits. 100 kilohertz, even wider. And finally, 300 kilohertz, I'm able to ignite with either lower energy or broader range, or I could even go to a higher energy than the capacitive discharge and end up with an even wider range of ignition of fuel flow rates for ignition. And this is just some imaging of that in chemiluminescence. Is it going to play? Sorry, 1 second. There we go. All right, so we could see in the 300 kilohertz case and the 50 kilohertz case, the discharge goes directly to the backward facing step and grows there pretty efficiently. For the low pulse repetition cases, I don't really see that. For 20 kilohertz and 10 kilohertz, I'm not getting, for 10 kilohertz, I only get ignition at the very end, 20 kilohertz earlier, 30 kilohertz earlier, but these are almost fully developed ignition events here. What I can see is for these different pulse repetition frequencies, I'll show better on the next plot. For different pulse repetition frequencies, I still had the same probability distribution, or it's shifted in terms of where those regimes are in terms of interpulse time. The ignition probability increased with power. There was almost no change with energy over a factor of 4 that we tried here, again with about 3 millijoules per pulse. I could define my regimes. And then if I looked at the time to ignition, I also saw a correlation between the high probability cases and the time to ignition, which in a scramjet makes sense because I have a limited residence time in my cavity. And once my residence time exceeded about 2 recirculation times of the cavity, 2 or 3 recirculation times of the cavity, I started to get a reduction in my ignition probability. All right, so you can see that here versus here. And so time to ignition and ignition probability are linked in the case of a scramjet engine, which is an important note to be aware of. All right, finally, we looked at the underlying mechanics forgive me, I'm going to go a little bit over here. I'd really like to show you some of these slides. So we took a first level approach, which I showed. We have the plasma energy deposition process and the kernel formation and development process. This ranges these timescales. And we took 3 different studies: optical emission spectroscopy for temperature measurements during the discharge, infrared measurements for ignition kernel temperature, and then OH-PLIF at 50 kilohertz for the microsecond timescale of radical dynamics. So this is a pretty typical optical emission spectroscopy setup. By the way, this work was mostly led by Steve Adams and Jared Miles in collaboration with Purdue University. Okay, so what I saw is when fitting the N2 second positive system, I could very easily tell the temperature. I should say this was in air. And what we found was very shortly after the first pulse, I got a rapid rise in the temperature. Then when I initiate the second pulse, I could see my temperature was already increased. So I'm looking at nanoseconds after each pulse initiation, and I'm looking at the second pulse. So this is pulse 1, and then at different pulse repetition frequencies, I can look at more pulses. So this is to say that in the first measurement, this is a marker for what the gas temperature is, not affected by that second pulse. So what we can see in this plot then is what is the temperature a certain time delay after that first pulse. For anyone familiar with OES, you know we can't look in this regime because there's just no light emission, and that's actually the subject of our further studies. But we can see that as my time between pulses increased, I would end up with a lower temperature, and I'd end up with my second pulse coming in after my first pulse had cooled down. And at different pulse repetition frequencies, I could see a very drastic difference in the peak rotational temperature after 10 pulses. So at 5 kilohertz or 10 kilohertz, after 10 pulses, essentially my gas hasn't changed temperature from its initial temperature. But when I go up to 15, 20, all the way up to 250 kilohertz pulse repetition frequency, I saw a drastic increase in my rotational temperature. So this is this pulse coupling effect at work. At high frequencies, I actually do get a very much higher temperature in between pulses and accumulated over the pulse burst. And I can correlate this with my ignition regimes. All right, so this was an air, and we pretty much saw a plot like this. But we figured that in a combustible mixture, there would be a slight slope here where I could get this build up because of chain branching kinetics, and that would be superimposed on top of this stair step from the plasma. And to investigate this, we did a OH-PLIF at 50 kilohertz, where the laser was shot down the end of our tunnel, and we interrogated this region of the discharge. This is the overlaid Schlieren and OH-PLIF imaging for that, with a false color map, of course. And what we find is at high pulse repetition frequency, I get a much larger and continuous region of OH, where at these lower pulse repetition frequencies, my Schlieren may show a lot of hot gas, but there's very little OH inside of that hot gas. It's a little hard to tell here. We'll look at these plots to tell better. So at low frequency, about 2 kilohertz, between pulses, I would return to about the same amount of OH that I had before any pulses. So essentially all of the OH would be more or less quenched. As I go up to 5 kilohertz, it's almost quenched, but not quite. Then finally at 10 kilohertz, I get the stair-step approach, and it just gets faster, 50 kilohertz up to 200 kilohertz. And I can see a very clear difference between these different pulse repetition frequencies in terms of the total amount of OH. I could also look at the average intensity per pixel, which means how much OH signal we got on average for each pixel that did have a signal. And what I see is for high frequencies, I get this really high super equilibrium amount of OH intensity. And that relaxed as my kernel ended up growing until they all kind of converge on this equilibrium signal intensity. So I can see that at high pulse repetition frequencies, I'm actually creating a much higher number density of OH than I'd have in a normal flame. And this is in line with the modeling, which I showed earlier. I promise I'm wrapping up. Here are some better images. We could see a very strong correlation. Here we see probability, and here we see how much OH we had in pixel count. And there's a direct correlation above this threshold of the OH concentration and the ignition probability. Finally, we did infrared imaging to look a little further downstream. These are the assumptions we don't have time for. And I, again, found a similar result, where at low pulse repetition frequency cases here, which had a low ignition probability, I had kind of a cool kernel. And as I increase my pulse repetition frequency, here I have 10 kilohertz, a pretty high ignition probability. And you can see I approach the temperature of the ignition kernel, and then it grows high in temperature according to the stretch rate and the radius of the kernel. But when I have a very high pulse repetition frequency, here up to 100 kilohertz, I could overshoot that temperature in the kernel. And I'd have a super equilibrium temperature in the kernel, which could last up to 4 or 5 milliseconds until I relax back down to my normal flame temperature. And so the persistence of this super equilibrium temperature was what we thought was new here. Okay, thank you very much for my talk. I apologize for going long. These are the conclusions. Our future work will be aimed at looking at more areas, multi-phase, higher turbulence. And I just want to note that we're hiring. So any PhD students or postdocs, please, we'd very much like to have you out here in Israel. It's a very nice place to work. This is an example of some of the studies we have going on. Here we're doing ammonia forming to improve combustion performance. We have a lot of exciting projects. So I hope that you'll come out or consider us, and I'll take any questions.
Okay, thank you, Joe, for the very exciting talk. Thank you. So now we are open for Q&A. I have got a few questions from the audience, and I will ask on behalf of them. The first question is from So Yang. His question is, in the TD test, looks like you used fixed energy per pulse. Then the high frequency one essentially have more energy input than the low frequency one. Is that correct? Should we adjust to make sure the total energy input is the same?
So Svo, I think this is the slide you were referring to. So each of these lines, let's remove that coloring. So each of these lines is an iso energy surface, let's say. The number of pulses determines the total energy. By changing the frequency, I'm changing the power, but not affecting the energy. Another way to think of it is each of these lines has the same total energy, but on the x-axis, I'm changing something like the duration, let's say. So for the 2 pulses case, I'd apply them in a shorter duration here, longer duration here. Same for each of these lines. So we're very careful to maintain the same energy and just vary the power. And that's how we were able to come up with this minimum emission power case.
Why is the ignition probability for the decoupled case higher than the partial decoupled case? What's the physical explanation?
So I'm glad you asked that question. And as you can tell, we did a lot of diagnostics trying to come to a conclusion on that issue. And this is the biggest open question. I think we all the people doing active research on this study, Tim Umbrello's group, and I really want to mention right now what we have going on is Tim Umbrello's group at AFRL and my group have an active collaboration. I should say we're funded by our respective DODs. So we're both working on this continuously to try to answer that very question, which we think is the most interesting. I think the closest that we've come to answering that might be here. So what I see in these black dots is my maximal pixel count in a small region around the electrodes of where I have OH signal. And when I look at that, this is the decoupled regime and this is the partially coupled regime. I actually see a slight drop in my OH number density when I go from the fully coupled or go from the decoupled to the partially coupled regime. And then I see it rise continuously in this fully coupled regime. And so this is a little hint of what's going on. Basically, what we've determined is this is not something that's happening in the plasma. The plasma does not seem to notice this partially coupled or fully coupled regime. And you can see that in the measurements we took in the plasma. Let's see. Yeah, here. You can see there's no real hysteresis here. But the problem is between 5 and 10 kilohertz, there's only a slight rise in temperature. It doesn't really quite reach the flame speed, even at those pulse repetition frequencies. So what we think is happening is that there is a fluid dynamic effect of one kernel being too close to another kernel that's just slightly downstream of it. And that this creates a pressure rise. Maybe you can see it in these images. So you can see here in this partially coupled regime, I do have some space between neighboring kernels. And I get this really fast growth in the beginning of an ignition kernel. And what we think is happening is that jetting motion is actually disturbing the flame structure before the previous kernel reaches the critical radius. And therefore, it is upsetting it at a very critical time, and that reduces the ignition probability slightly. But as I said, I think this is one of the most interesting questions happening here. I don't think it's a plasma phenomena. I think it's a purely flame phenomena. And we haven't been able to escape it. Actually, in the study I didn't show here that was conducted at AFRL, they varied the Lewis number, thinking that should obviously change these coupling regimes. And it only had a minor effect going from Lewis number of less than 1 to more than 1. I mean, they didn't vary it so widely. I think I remember it's from slightly under 1 to around 2. And it didn't really change these regimes. So it's a flame phenomena, and it's one that I think requires further study. And I'm glad to have the chance to talk a little more about that.
Okay, thank you, John. Following this question, actually, Dr. Matt Kokak also asked a question about this. Have you considered developing scaling rules for defining the thresholds for the transition between modes, fully decoupled, partially decoupled, and so on? This could go a long way towards predictive capabilities.
Right. So as I showed, we did that this scaling thing for the growth rate, which was pretty straightforward to do. Probability is a little bit harder. We do have a theory on it. It's not published yet. We're not quite ready to confirm it. And one of the last steps that we had in confirming it was changing the energy per pulse. Now, as I showed with the 10 kilovolt pulsar, we didn't really have the freedom to change the energy per pulse much. So the work I showed when we were changing that in these slides, let's see if I can bring them up here. We just took this data about maybe a month or two ago here at Technion with our higher voltage pulsar. And so this was kind of the last piece of the puzzle before trying to put together a larger theory. And I think we'll be able to do it. And basically, there's 3 time scales, or you can call them spatial scales, which matter for ignition probability. There's the there's the spatial scale of the initial region where you deposit heat and radicals, which we defined by the OH-PLIF imaging. So there's that initial deposition timescale, then there's the flame growth timescale, and then there's the flow timescale. And if you have the right combination of those 3, you'll have high ignition probability. And if the combination is wrong, you won't. And so by combining those 3 timescales, I think we'll be able to come with a scaling parameter that can account for the ignition probability in all of our cases. We're close. We just needed a little more data, a little more time before we're ready to show that. But that's a good question, man.
Okay, thank you, Joe. The next question is about how was the ignition probability obtained?
We did 20 pulses, 20, well, not 20 pulses, I'm sorry, 20 individual ignition events. And then we looked at how many ignited and how many didn't. We have Schlieren imaging for all of it. Usually we were imaging at 50 kilohertz. Now, I think what the question might really be asking is, it does appear to be very hard to tell between an igniting and a not igniting case in the Schlieren imaging when you're on the border. And you can really tell by the horizontal expansion rate. So if you look at the horizontal expansion rate of the kernel, when you have an ignition event, it expands horizontally, where if it's not igniting, it doesn't. And then we use a binomial probability distribution based on a number of 20 cases to put those error bars there for the ignition probability.
Okay, thank you. So the next question is, have studies been done to see if the recirculation vortices created in a scramjet had deleterious advantageous effects on ignition by the NPHFD?
Well, you saw the work that we showed. As far as I know, this is, well, this and some work that was done in Stanford looked at nanosecond pulse high frequency discharge in the scramjet cavity. You can see here, we were looking at it. Now, in a work published by Tim Umbrello and Steve Hammack, and I'm sorry if I forgot the other co-authors, in the last symposium, they looked at a capacitive ignition event in a scramjet. And what they found is that based on the location in the cavity, this was a huge determining factor for whether ignition stabilized or not. And basically what you need to do in the cavity is create something that can live right behind the step. So if you look at all of these cases, the discharge needs to make it to the step. And once it's at the step, only then can it grow laterally and downstream. If it doesn't stabilize at the step, and you can see all of these individual ignition kernels, they're just not stabilizing. And so they just get quenched. But once they're at the step, they slowly expand in that recirculation zone right behind the step until they can fill the cavity, and then they can ignite the main flow. I'm not sure if this answers your question or not, but I think there's a lot of interesting dynamics to look at in the scramjet cavity. We certainly hope to do more work in this area.
Okay, thank you, John. And the next question is from Punjab. He asks, the pulse frequency given a characteristic time, which should be comparable to some plasma chemistry or key radical lifetime scales, subject to local turbulent intensity and flow, to make the ignition strategy functional. Have you looked into the threshold frequency and the key chemical time scale controlling local kernel extinction?
Yeah, so that's a two-part question, I guess. So the first question is, can you just look at kinetics and get an answer for this? And I guess the result of that is, I mean, if you pick the exact right conditions that match your results, then yes. But looking at it in a fully 3D coupled sense, no, it's very hard to do that. There was a recent paper, and I'm not going to get the names right, so I'm not going to mention them, but in the proceedings, in the recent proceedings where they did full 3D simulations of ignition by pulse discharge, not for our conditions, but for conditions performed by Diana Lacoste and Christophe Lowe a few years ago in their mini pack burner. And you could see the timescale of recirculation and the 3D dynamics of the plasma region are really important, because when, let me go to my next image here. So you can see that for the first discharge, I always get this ring of OH. And that's because in the center of the discharge, I have very high temperature gas. It needs to get to the edge in order to recombine into OH. But after that, I get this toroidal structure. Now that structure is disturbed when I have multiple pulses, but let's just talk about for a single pulse. So for a single pulse, I form this toroid or donut shape. And what happens then is I get flow recirculation back to the center of the toroid. And you have to take into account that type of flow in order to properly model this. So that was done in this recent proceedings paper. I really encourage you to look at that. And they showed that you could get, they showed you could simulate ignition or not ignition. They showed that, importantly, if you only treated the plasma as a thermal energy deposition, or if you treated it as split between thermal and radical creations like we do in our modeling here, where we're looking at O atom, with the same energy, you need to model the kinetics of radical formation in order to properly capture ignition. So if I pretend this is just thermal energy addition, I will not properly capture ignition. If I do thermal plus kinetics, then I can properly model ignition. And so what it comes down to is NRP plasma a thermal process or a kinetic process? The answer is yes.
Okay, thank you, Joe. The next question is from Wanhan from Edinburgh University. He said it's a very impressive talk. His question is, which OH-PLIF method, 2D OH-PLIF or tomograph OH-PLIF, did you use to characterize the flame kernel? Can you give some comments on the limitations of 2D OH-PLIF in capturing 3D kernel development?
Yes, so this was 2D, not Tomo. The limitations are a few. First, we can only capture it from one perspective, right? So I can imagine my laser sheet is kind of the same as the image here. Now you can imagine I'd like to have a sheet kind of perpendicular so that I could look along the direction of the electrode, and then I'd be able to see the whole donut. Here I have to assume there's a donut, but there might not be a donut coming in and out of the screen, right? I need to look from the other direction. So that would be one thing that would be very helpful to see. But I would say the biggest limitation, and you can see it maybe better here, is if my kernel happens, I can see a big OH region here, and then all of a sudden here it's gone. Now I have to assume that it got quenched, but it's very possible that it just drifted outside of the plane of the laser. And so we did, for each of these PLIF experiments, we did 10 different ignition events at the same condition. We tried to pick ones that were really representative, but when you have a small OH-PLIF OH region in an ignition kernel, it can always drift outside of the range of the laser sheet. And this can cause, you might be seeing something that's not there or vice versa. And I'd recommend to take a lot of repeated experiments to get around that. So I guess that's my answer. Tomographic would be great. I hope somebody does it.
Thank you, Joe. One last question from So Yang. He asks, the industry has very high resistance to actually use the plasma system combustion technology. In your opinion, what are the major bottlenecks and what might be the future directions, such that the industry can use the plasma system combustion?
All right, well, let's distinguish between the auto industry and the aero industry, right? So as I said, I'm working closely with AFRL. I don't want to speak for them, but I think that they are working very closely with the companies developing scramjet technology. I'm not saying anything. I have no other information than that as a scientist, right? But I assume that as that scramjet industry develops and these things become operational, what we learn now will have an impact there. But talking about the more traditional industries, in terms of gas turbine engines, as you know, they're getting leaner and leaner and leaner. I think that they will have to start thinking of some of these technologies when they build. And I would say the bottleneck is, as long as what they have now works, they're not going to switch to something else. So if regulations get to the point where they're pushed further and further, then you might start to see, I think, these technologies take a role. I think automotive is a little bit different. And you see some of these advanced engines start to come out because they really are getting pushed in terms of regulation. And so, for example, a company like, I think Mazda is doing like a spark assisted HCCI engine. And when you really need that type of ignition control, or you want to work with a company that's doing innovative things like that, I think there is an opening to come in. But I'm not sure. I'm not sure if I have a better answer. I do work with several companies in this work. For example, I work with an aerospace engine company, which is actually doing Wenkel engines, which I think is really interesting because, as you know, in a Wenkel engine, you have flow being pushed by the rotor past your igniter. And that seems to be the perfect place to use this type of discharge. And I think it's a small company, and I think they would be very likely to take on this type of discharge if they do see a drastic improvement. So I'll let you know if they start developing it in large scale.
And one thing I want to say that Joe, and when you were at Princeton, we really only look at that the single pulse or even uniform discharge about that the dynamics and for single pulse and then the chemistry. But now that after graduation, you really take over in another dimension, which is looking at the pulse-pulse interaction and the frequency dimension. I think this is really interesting. You make this a kind of a quasi-steady state and towards to that the dynamics of plasma ignition. So one thing that really intrigued me that you have formulation about that the plasma expansion volume correlation with that the number of pulses and the time. And in that graph, have you included that the combustion itself or just in air?
Let me see if I can bring up the correct graph just to make sure we're talking about the same thing.
Yeah,
These ones?
No, you're the one graph you're showing. No, not that one. The one graph you're showing that the estimation about that the expansion.
Yes. Okay.
That
So
one,
yeah, the answer to that is no.
right.
Because
All right, this one, yes. I saw this one
yeah.
is very beautiful. And then, all right.
Right. So what we're doing here is we are just trying to look at the moment the discharge is completed, how large is the kernel. Now, what goes on after that is, of course, typical flame growth dynamics. So we didn't extend the model there. So this is just trying to predict the cross section at the moment the plasma stops. Or I could say you could also look at the derivative and say it's the growth rate while the plasma is on. And we did see that we needed to include kind of, I mean, I didn't call it flame speed because it's not flame speed, but it's a growth of the ignition kernel, and it's happening at an order of magnitude faster than the flame speed. And so, we included it as if it were a flame speed, at least for early time, and it's superimposed upon this rectangular shape, and we assumed that it was kind of a sphere. Probably we should have used an oval geometry to get a better assumption, but we got a pretty good fit to the data anyway. But no, we didn't continue this prediction beyond the end of the plasma. And we expect, obviously, you can't use just one value of flame speed to do that properly. You would have to do, as you'd have to have the flame speed as a function of stretch rate. And and of course it's not a smooth laminar flame as you've seen in the images.
Right,
so we didn't take it there.
Another one that is I try to discuss that if you have a pulse discharge, particularly in nanosecond plasma, right? Many of the electron energy goes to that vibrational excitation of nitrogen. That energy comes back to rotational energy, take about a millisecond and probably sometime longer to come back. So I'm wondering that time scale should be considered in thinking about that what is that the energy deposited, because that you take a longer time for that thing to come back, and so whether that they can give you some kind of interpretation about that when you have partially coupling and then a different frequency, and that can give you different OH concentration, you decay, because whether that energy is at that time scale that's stored in vibrational not come back to the rotational. Just try to give you some thoughts about it. I thought that your talk is really beautiful, and I'm very impressed.
Okay, thank you. Well, due to the time limitation, we have to stop here. If you have more questions, please feel free to contact Dr. Lefkowitz. Thank you for your participation. It's a wonderful talk.